Recording.
Hello.
Yeah,
Hello. Yeah, Sindhu
it-
ma'am told she'll be joining from the
yep,
second person.
yeah,
Told us to continue it.
yeah. Okay, I hope the screen is visible.
Yes, yes.
Okay. So good afternoon, everybody. Today's topic for technical seminar is applications of transfer learning in object detection. Uh, so this is what we'll be going through, and expected contents of the slide are introduction, literature survey, where I'll be explaining the papers that I read, the concept of transfer learning, procedure on how it must be done, the methodology, what are the case scenarios where transfer learning is applied and how it must be applied, the case study of a particular problem, and result analysis, along with conclusion and future work, with and signing off with references. So, what is transfer learning? Transfer learning is an area of machine learning where a model learns some features or the data that another model has learned. That's the most basic definition that one can give of transfer learning. It is the transferring of learning from one model to another. So yeah, so here you can see a model which has been trained on a very large data set, has the ability to learn a lot of features, which we, on the other hand, if we have a small data set, can't learn. Okay, according to Andrew Ng, the next driver of ML success is transfer learning. We will see to that why it has been regarded as such a high position and how exactly it happens. Okay, moving on to the literature survey, there were five papers that were researched on. The first one is image classification using CNN. This paper was read only with an aim to establish the fact that CNN are our way to go for images. So if you are dealing with images, image classifications, then CNN is the place we need to go. I will be diving into what CNN is and the basic working of CNN. And the next is using deep learning for plant-based plant disease detection. And this was in 2016. And so here they established the fact telling that transfer learning, if used correctly, that is, if it is in with respect to the case scenarios where it will fit properly and proper fine tuning is done, then we can achieve very high accuracies even though we have a relatively small data set. That was about the second paper. The third paper is a study on CNN transfer for image classification, where they saw what model is suitable for transfer learning. So there are many models that are built for transfer learning. So there is Inception V2, there is Inception V3, there is AlexNet, there is Google LeNet. They made a comparisons of those and told uh, that a model is suitable for transfer learning, and they explained the nuances of it. So that was about the third paper. Fourth paper, moving on, is they use transfer learning in diabetic retinopathy image classification, and this is in 2020. And they explored the architectures of these images. I mean these networks. And one thing here to note is that a basic question: why should transfer learning be used? Why can't I train a neural network on my own? So we will be case studying an Inception V3 model, which is trained on the ImageNet. So ImageNet dataset has around 1.2 million datasets with 1,000 classes each, and the model that they built is so complex that if I had to do it in my laptop, it would take me around months, at least 2 to 3 months. Or if I say no, I don't want to compromise on time, and let me gain the necessary resources to train that neural network in an efficient manner, I would be requiring almost 3 lakh rupees. That's for buying the GPUs, that's for buying the storage, and as well as the GPU and RAM. So they explained the architectures and how transfer learning is applied and how the accuracy got up when using transfer learning. And the last paper is, do ImageNet models transfer better? That means they made a case study that if neural networks are trained on ImageNet models, will they perform better in transfer learning? So suppose I built some neural network, some small neural network, and trained it on ImageNet. Will my model be able to transfer better if I trained on the ImageNet dataset, or if I trained it on some other random dataset? So here more focus is on the ImageNet dataset rather than the transfer learning. So they said that they concluded that any model that is built on ImageNet has very good accuracy of transfer learning. That is, when it's transfer learned, the accuracy actually goes up. Now, before we move on to the concept, I would like to go on to the case study and start executing some codes, because executing that code and running it takes some time. So I might as well do that. Uh, okay, so we'll get back to the code later. I'm just executing it. We will get back to the code and see how it all works. Right, I hope the screen is visible. This what you're seeing on the screen is the architecture of a CNN, convolution neural network. As its name says, convolution neural network. So there are two topics to understand here. One is what convolution is, and one what pooling is. So convolution, it applies some operation on the image and gives another image, or this is with respect to the CV2 or the uh, features of the image. What I mean to say is, if I take an image and I pass a horizontal convolution matrix on it, and then I merge them, I will be getting an image which has the horizontal lines extracted or highlighted. And then what pooling does is, it there are different types of pooling of here, which we'll be studying max pooling. So what it does is, if you consider a 2 cross 2 matrix, and you're applying a pooling on it, max pooling on it, what it does is it takes the highest pixel value of that matrix and creates a new matrix. So you can see the size difference here. So the convolution and ReLU here, ReLU is an activation. So convolution, it highlighted some features. The pooling reduced the size of the image. Then there is another convolution, and pooling further reduce the image. Then, and so on, so on, so on. And finally, we connect it to our normal deep neural network, which takes the input in a flattened way, and then has a fully connected dense layer, and softmax is just used for classification. That's the it converts the value into probability. So this is the general working of how a CNN works. This was just given to an overview because we'll be using ImageNet. Now, when we move further, this is how transfer learning happens. So if you consider this is a convolutional neural network that has been trained to detect dog or cat or basically object detection, what we do is, suppose uh, there are this model was built to detect objects. My use case is to detect cats or dogs with a very relatively small data set. So this was trained on 1.2 million data points. Okay, 1.2 images, that's a lot. But I have around 1,000 images or 2,000 images. So when we talk in terms of traditional perspective, you might ask the question, why don't I train my neural network on 2,000 images and call it a day? But that's not, you can do that. There's no harm in doing that. But what we fail to achieve is that we might not be able to classify images properly. That's in the validation. What I mean to say is, suppose I trained a neural network on classifying cats and dogs, and all my images are upright. But then a new image pops up where the cat is reversed. That time my model might not be able to detect that it's a cat. And now you might also argue that you can use image augmentation. But still, what if there's an image where there is dog and a cat, or there is a human or a dog which is positioned in such a way that it looks like a cat, right? So the uh, leverage where we can get from this is the Inception V3 model is trained on ImageNet, which has 1.2 million images of different types. So the Inception V3 model has captured some interesting features that our data set might not possess. Okay, that's why transfer learning induced, and here is how transfer learning is happening. So this is the object. This is the architecture, and this is with specific to object detection of that model. But what we do is we cut off the layers here, and we freeze everything. We freeze the weights and biases of all the stuff it has learned here. Because in a convolution network, the first layer, as we progress, we move on to highly generalized features to highly specific features. So maybe this layer will only detect the lines and edges, and this will detect faces, and this will detect body. And finally, it will detect it's a dog, cat, or any other class. Okay, so what we do is after we cut it here, we create our own dense network. And then here we train the model. We make sure that we are not training any of this because this is what is important. The model has learned so better at classifying basic, that is very general features that our data set doesn't have. So now when we train it here, we will be getting very high, comparatively very high accuracies than training on a traditional way. These are the strategies for choosing what type of transfer learning, not what type or what methodology in transfer learning. So this is the size of the data set and the data similarity. Now, when I told object detection, so I have an object detection. Consider this a set of object detection where all these classes are there, and in that I have cats and dogs. So I can fine tune my model to use transfer learning for detecting cats and dogs. But if it is completely other domain, maybe regarding some heart or diseases, or maybe lung cancer or something, then our model might not be able to perform well. So these are some case scenarios. We'll go through everything. So if the size of the data set is very high, but the data similarity between the chosen problem and the data set on which the original model was trained on is very low, then we train the model from scratch because there's no use of transfer learning here. But if the size of the data set that we have is small and the data set similarity is also small, then this is a very good case of transfer learning. We can just fine tune the lower cases. So in our example, we will be tuning our final layers to detect cats and dogs. And here, if the size of the data set is very low, but the data similarity is very high, then we can further generalize, further increase the accuracy of our model by fine tuning the output dense layer. Okay, this is the lower layers and this is the output dense layer. But now, if the size of the data set is very high and the data similarity is also very high, we fine tune the pre-trained model itself. That means if we just run our data set over the model, then we get very high accuracies. So these are the four cases of transfer learning. And moving on, the procedure. This is the very basic procedure what we use in transfer learning. One, we import the model. In this example, Inception V3. Then we remove the last layer according to our use case. So we remove the last layer and then we freeze the weights and biases that we don't require. So we want to learn what the Inception V3 learned in understanding the base feature. So we freeze all of that, and then finally we add new layers or another deep neural network architecture at the end, like how you saw it in this place. And then we start training the model with respect to a problem. So this is the procedure. So let's move on to the case study here. uh, I hope the screen is visible. So let me just go ahead and explain the code. We are just importing the basic libraries, the layers, and the model, and we are downloading the Inception V3, a specific weight version of Inception V3, and then we are downloading the. Okay, here is where we are. Uh, this part is being explained. Okay, so this part is being explained here, the cutting part. So here we trained pre-trained model include top equal to false. That means we are excluding the last layer, and we are loading the weights for this model of with the local weights file. That's the one we took here, the no top file. No top h.h5 is basically uh, it has all the weights of the inception v3 except apart the last layer. Okay, and for layer in this model, we are making everything trainable equal to false. That means we don't want to touch those layers of the neural network, because that's what transfer learning is all about. We have to learn from these layers, so hence we don't train them, we don't modify them at all. And this pre-trained model summary is commented because it is a very large architecture. I might as well show you if you want. It's a quite large list of how the Inception V3 was built. So executing that on my uh, on my laptop is really a cumbersome process. So you can see the layers here, the activations and all that. So it goes on and on and on and on and on. As I told you, it would almost take me 3 lakh rupees to get the necessary hardware for building all these. So it's still going on and on and on. That's how complex this inception v3 architecture is. Okay, so that's done, and we take the last layer, we get the last layer by using the keyword mixit7. That's here some con 2d or something mix7, and then we printed the last output layer output. Okay, that's down. Right, so the shape is 7 cross 7. That's we are getting an image of 7 cross 7, and we have 768 neurons over there. Okay, now here here's what we are doing. Now this cell explains the part of adding our own architecture, or basically this part. Okay, so we flattened the output of the last layer. We added 1024 neurons, and then uh, okay, here I just let me just uncomment this. So dropout here is an interesting concept. We are using dropout because sometimes when we are transfer learning, there are chances of our model being overfitted on the specific use case we are trying to do. That means when neurons are stacked, there are chances that they have the similar weights and they learn the similar weights, and we don't want that to
Nitin,
happen. Yes.
Nitin, can you
Yeah.
please share your PPT in the group?
Oh yeah, sure.
Everyone, all four.
Yeah, sure. Yes. Yeah,
Okay.
so moving continuing the draw, what this does is 0.2%, that is 20% of the neurons in that layer are dropped. That means there is no activation there. Those neurons are basically dead. Okay, this is just to make sure that our model isn't overfitting. And next we move on. This is just the data creation part where we are putting everything into folders and everything. So we have 2000 images that belong to two classes for training, and 1000 images that belong to classification. And here is where we are fitting the model.fit. And you can see I guess this is not using the dropouts. Okay, so here is where the model fitting is happening basically. And once we see the output, we'll be able to understand if our model had performed well, or if it didn't perform well. Did it overfit or what? It's not connected to a runtime. Okay, but by the way, I'm using Collab just to make sure that I have enough GPU to make this stuff faster. While this is being executed, let's just have a look at how the training is happening. So this is the accuracy on the test data set, and this is the validation accuracy. And yeah, so now that this is, we see that the training accuracy is increasing, and the validation stays constant. So this means that our model isn't overfitting, and this is due to the result of using the dropouts. If there were no dropouts, then what would happen is training would increase and training curve, that's the red line, would go down and down and down, but the validation would remain same. So this is the case of overfitting. Okay, that was what I wanted to explain here. And continuing on this, so you see the accuracy is staying same, and validation accuracy. This is basically a plot of what's happening here. So this was an demonstration of transfer learning for detecting cats and dogs using the Inception V3 model. So that was about it. Uh, and it's 25 minutes up. I pause for questions. Yes, no? Okay. So finally, to conclude, transfer learning is a really, really excellent concept. Speaking of which, with respect to you know, so it's more like an open source community. So people like Google and Facebook, they have access to very large amount of resources, and an average person doesn't have that much resources. So using models like these, we are transfer learning, we are able to get better accuracies with a very low data set. Okay. Now, when I train the example that I showed in a traditional way, I will be getting very good accuracy. Maybe I might get around say 80% accuracy, 85% accuracy. But what I fail is to capture very new images. As I told you, if the cat is upright, upside down, or if dog is almost sleeping in the position of a cat, then my model might misclassify. So it saves a lot of time and money, as I told you. Instead of doing it 2 months, I could do it in 5-10 minutes. And money, of course, there is no money involved here because I'm doing transfer learning. But if I were to use the resources, it would almost cost me 2.5 to 3 lakh rupees, and high accuracy as compared to the traditional learning. In the future work, there might be more work required on the you know process of what parameters must be fine tuned. Should it only be the last layer with respect to the problem we're solving, or should I do any manipulations in the initial layers? These are the areas where more research is required on the fine tuning. And yeah, so that was about the transfer learning, and these are the references used for doing the literature survey. And thank you.
Nitin,
Yes, sir.
I have a couple of questions for you. So
Yeah,
let me
sure.
start from the second to the last slide.
Okay.
So second to the last slide, you said you calculate the accuracy, right? So if you can go to the code, I think
Mhm.
validation accuracy was a little bit higher than accuracy. What's the what? I mean, why is it so?
Okay.
If
Let me just go there. Okay, here.
yes, just
Yeah.
check
Okay. Hmm.
accuracy versus validation accuracy. Which one is higher and why? Can you justify?
You mean to say you're asking why this is already higher?
Yes.
Okay, so that's the point of transfer learning. So even though we trained on a very small data set, so the model itself was actually able to classify without, see, we are training our model on cats and dogs, right? But the
Mhm.
Inception V3 has already trained on 1.2 million images which have cats and dogs in it.
Mhm.
So it has learned those features. So that's
Okay.
it.
So can you, yeah, okay, it's fine. Can you tell me how you calculated that accuracy? Do you know the fundamental formula for that to calculate
I,
accuracy?
I do. Accuracy is, it is the correctly classified instances of the total
Hmm.
instances, and we use the concept of confusion matrix where we see the precision, recall, the F1
Okay,
score.
so can you express it in terms of TP minus whatever? Can you tell the formula quickly?
Okay, F1 score is based on precision and recall. That's precision plus recall by. Uh, okay, I might be missing on that
Okay.
formulas.
Okay, it's okay, it's okay. You look into that later, okay?
Yeah.
So another thing which I wrote down was you said that the model, we want to ensure,
Mm,
I mean, you said somewhere about overfitting. So my question is this,
yeah.
okay? How do you know that your model is not overfitting?
Oh, we see the, as I told you, if we have time, let me just execute it. Let me, just a second. So let
No,
me
you can
just,
give a
okay.
generic view. How do you know that a model is not overfitting?
Okay, so when a model performs very well on the training data set and very bad on the validation data set, it means that our model is not classifying on the data that it hasn't seen before. So it has learned the features very specific to the training data set that we have given. Okay, that's where we can see the
Yeah.
overfitting. I would like to show you the graph. Let me just decrease the box. Just say 5.
Yeah, so it's okay. Why you show the graph? So can you tell me the difference between epoch and iteration? Because I wanted to ask you why you have chosen 20 epoch. Are you not overloading your PC even or your whatever? So
I am
why can you
I'm
differentiate
running.
between epochs?
Okay,
I know you are.
sorry.
No, differentiate between epochs and iteration.
Yeah, so epoch is the one complete cycle from the starting of the neural network to the end of the neural network. So all the training and going back with the and updating the errors, weights and biases, that's the complete stuff of uh, one epoch. But iteration is, I'll show you, because since we cannot train or everything together, so there are 2000 images which I cannot do. So I am training only 100 images at once and 50 images on the validation data set.
Okay, good
Okay,
boy. My
that's
last
the
question
iteration.
is last
Yeah.
question. Enough. Last question. You said something about age detection, right? In image processing. Age
Yes,
detection, right?
yes.
So can you give me any of the age detection algorithms which you saw in that paper? Anyone?
Well, while they didn't explain any edge detection algorithm, it was they passed the convolution layer. I mean the convolution matrix. So if we want to detect horizontal lines, and in a 3x3 matrix, the middle row will be 0, 0, 0. If you're learning vertical lines, then the horizontal vertical middle row will be 0, 0, 0. So that highlights this stuff.
Okay, fine. Maybe they didn't highlight any age detection algorithms. Okay, maybe. But yeah,
Yeah,
at least the commonly used ones are you have Kani age detection and then you have suburb.
yeah.
That's it. And the first paper which you referred is too old. Why did you refer that?
Uh,
2014.
that was just to explain or to establish the fact that convolutional neural networks are the place where we need to go when we are going for image processing in deep learning field. So it was just
I'm
to
done.
establish that fact. That's all.
Okay, good.
Yeah.
I'm done.
Any further questions?
Yeah, no questions from my side. Few questions
Okay.
which I had was asked by Victor sir itself.
Okay. Okay. Fine. If nobody else has any questions, I shall end this session, and please rejoin back on the same link where the next person will be presenting. Right. Thank you everyone for your time.